Example 3 in 9.1 throws a bit of a curveball right off the bat. And it's that the function that they gave us, this y equals 4x minus 5 over x minus 2, is not in the form that we can talk about, which is y equals a over x minus h plus k. And the problem with that is that we see the variables in the numerator and the denominator. So when we do talk about transformations, what we want to make sure that we can do is manipulate it so that it looks like that form. And there's certainly many different ways of doing this. You can manipulate the numerator so it's divisible by the denominator by adding and subtracting a number within, and I'll show that technique in one of these examples. But I think the better technique by far is to use long division. Because if you remember, and it's been a while, I know that we talked about how if you take a polynomial and you divide it by x minus a, you get the result of the division, which we call the quotient, and then you have the remainder that is yet to be divided. Now, really what we're looking at, and I'd like to make this kind of, I hope, a little bit clear, is that this has a very similar form to that, right? R divided by x minus a. I've just put the, it's an a in a different context, which I know can be a little bit frustrating. And what I'd like to do is just actually do the long division. And I'd like to show you how easily or how well this works. So using our technique from chapter 4, I'm going to put that 4x minus 5, that's the actual polynomial inside my division symbol, and then x minus 2 is going to go on the outside, and I'm going to divide the leading term by the leading term of the divisor. So that's 4x divided by x, which is 4. When I take that result, that 4, multiply it back on to my divisor, I get 4x minus 8, and I'm going to subtract those numbers. And I'll put a bracket around there like I usually do. The 4x cancels with the 4x by design. Then I have negative 5 minus negative 8, which is positive 3. Now, positive 3 doesn't have a variable to it, so I can't divide that further. And if I attach, if I'm going to use the division statement here, that's this that I'm squaring in blue, I can say that 4x minus 5 divided by x minus 2 is equal to 4. That's the result of the division that I put an asterisk beside. And then I'm going to add that 3 that is yet to be divided by the x minus 2. Now, what's really important is that the right-hand side, if I manipulate it just a little bit and write it as 3 over x minus 2 plus 4, now students can see that generally and identify that a is equal to positive 3, h is equal to positive 2, and k is equal to positive 4. And then based on those parameters, we know that it's a vertical stretch by 3, it's a horizontal translation 2 to the right, and a vertical translation 4 up. And then we're right back to what we did in example 2 or example 1 without the translations. So, one of the hassles in this question is how do I go from, basically just a polynomial divided by a polynomial to that rational form? And I'd like to show you the other way of doing this, even though it is not my preferred technique. I think it's important to see both. I can write this as 4x minus 5 divided by x minus 2. And I just want to write over here that 4 times x minus 2 is 4x minus 8. And the reason why this is so important is what that means is that 4x minus 8 is nice and evenly divisible by x minus 2. And so what I'm going to do is I'm going to try to manipulate this fraction so that it contains 4x minus 8. And the way that we do that is that in the numerator, we subtract 3 because negative 5 minus 3 is negative 8, but I have to also add 3. And the reason that I have to do that is because that is equivalent to 0. I basically added 0 onto this fraction, so I haven't changed the value. Now, what that does to the fraction, and this is kind of some, weirdly kind of optional math, I'm only going to combine the negative 5 and the negative 3. So now I have 4x minus 8 plus 3 divided by x minus 2, and I'm going to now break that fraction apart. I'm going to write it as 4x minus 8 divided by x minus 2, and then I'm going to add 3 divided by x minus 2. Now, I can get away with that because it works in reverse, right? If you look at following these steps from the bottom to the top, that step makes sense, right? They have the same denominator, so I can combine or add their numerators. But the advantage to this step is that if I do a little bit of factoring in my first fraction, what I get is a factor that cancels. This x minus 2 will cancel with this x minus 2, and then I'm left with 3 over x minus 2 plus 4, which still yields a is equal to 3, h is equal to 2, and k is equal to 4. Now, I do not prefer the method in black, but it is super valid. It's a little bit similar to the completing the square technique that you learned ages ago. I do greatly prefer the long division technique because at least it makes all that work we did in chapter 3 pay dividends now in chapter 8 as well. Okay, all the way back though, now that we know what A, H, and K are, we can see that in the graph, there's certainly a vertical stretch by 3, but most importantly, I would argue, we know that this graph has been shifted 2 units to the right and 4 units up. And so I just want to write that the 2 units to the right is what's moved my vertical asymptote, and the 4 units up is what has moved my horizontal asymptote. And I don't want to belabor that particular, graphing too much because we did it in 2 examples. Example 3 is in here to show us how to convert from, maybe a general rational form to that transformed rational form.